Alright, physics students, today we're going to learn about gravitational potential energy and the law of conservation of energy. And we're going to start out with potential energy here. Yesterday we talked about kinetic energy and work. Kinetic energy being the energy of motion and work being a force pushing through a distance. And in order to do work, you need to have energy. If an object gains kinetic energy, it's because you did a certain amount of work to it. But both of those quantities are measured in joules, just like potential energy is going to be. Gravitational potential energy is energy that's stored due to its height, the height of an object, the gravitational field that it's in, and the object's mass. You can store that energy, but if that object starts to lose height, it gains kinetic energy, and it can be useful for doing work. So anyway, we're going to take a look at an example here, and we can see we have a 1,000 kilogram boulder that's 20 meters high in the air. It's on a cliff that's 20 meters high, and we want to know how much potential energy does that boulder have. So our equation for finding potential energy is PE equals mass times gravity times height. And the mass needs to be in kilograms. Gravity, G, is just 9.8 meters per second squared, and height is in meters. So this is a pretty simple plug-and-chug type problem. You put in 1,000 kilograms for the mass, since that's our mass, and 20 meters is our height. So we multiply times 9.8 meters per squared times our height of 20 meters. And our final answer is 196,000 joules. So that is how to find the potential energy of an object. So let's move on to something that's a little more complicated, and that would be the law of conservation of energy, or as I like to call it, LOCE. So anyway, basically the law of conservation of energy says that energy cannot be created or destroyed. You can only change its form. So you can have an object that has potential energy, but it starts to fall down. As it starts gaining speed, it's gaining kinetic energy and losing potential energy, but the total amount of energy is still there. We call the sum of kinetic energy and potential energy the mechanical energy. So I can write that as ME, mechanical energy, equals kinetic energy plus potential energy. So we're going to take a look at a problem here. Using the law of conservation of energy, how fast will that 1,000 kilogram boulder that we had in the last problem be going once it hits the ground? Not after it's hit the ground and come to rest, but as it's hitting the ground, how fast is it going? Now in Chapter 2, we used to do the problems using delta x, v, v naught, a, and t. And if it was in more than one dimension, we had to do that for both our x and our y variables. But the law of conservation of energy makes this a little simpler. So we start out knowing that the amount of mechanical energy that exists up here at the top, we'll call that ME1, is equal to the mechanical energy that we have down here at the bottom, ME2. Now, saying that ME1 is equal to ME2 is true, but it's not very helpful to us mathematically. So we need to be a little more descriptive. Now remember, mechanical energy is kinetic energy plus potential energy. So really, the mechanical energy at the top is equal to the kinetic energy that we start with plus the potential energy that we start with, and that is equal to the kinetic energy that we end with plus the potential energy that we end with. Now even this, while again being true, is not as helpful to us as we'd like to see. So we need to remember, what are the equations for KE and PE? Well, 2 days ago we learned the equation for kinetic energy is 1/2 mv squared. And because it's our beginning situation, we're going to say V1. What's the initial velocity? We're going to add that to our mass times gravity times height times the initial height, height 1. All right. Then on the other side, it's going to look exactly the same, except I'm going to put 2's instead of 1. So that's going to be 1/2 mv2 squared plus mgh2. All right. So you look at that equation, and you're like, okay, there are a lot of things in there. What are all those things? We've got mass, we've got velocity, initial velocity, we've got mass, we've got gravity, we've got initial height, mass, our second velocity, mass, gravity, and our final height. So if we look at the drawing, where do those things go? Well, my height of this cliff is 20 meters. So the boulder is initially 20 meters high, so h1 equals 20 meters. And when that rock first starts to fall, its velocity is 0. Now at the bottom, we want to know what that velocity is. That's velocity 2. But we also know that the height here is 0. So we look at what we know there, and we also know the mass is 1,000 kilograms. And then we look at our equation. And you're like, geez, that's a lot of variables. I don't want to do all that work. But here's the nice thing. A lot of times, some of those terms just cancel out. So take a look here. Our initial velocity is 0. Which means that our initial kinetic energy must also be 0, because if that's 0, the whole term goes away. So I'm going to cross that off. And our second height, h2, is also 0. So this whole term over here cancels out as well. So what I'm left with is mgh1 equals 1/2 mv2 squared. But notice I have a mass in both of those terms. If I divide both sides by m, which I'm allowed to do, those masses just cancel out. Now, mathematically, you might say, why can I, just get rid of mass? Doesn't that matter? But think back to when we talked about gravity and free fall back in Chapter 2, and we talked about the fact that mass doesn't have any effect on how fast an object falls. A large object will fall just as fast as a small object as long as we neglect air resistance. So the mass shouldn't play any part in how fast that boulder is falling. So what I really end up with here is gh1 equals 1/2 v2 squared. I'm going to multiply both sides by 2 to get rid of the 1/2. And I'm going to take the square root of both sides to get rid of that exponent. So now I've got the square root of 2gh1 equals v2. Well, I know h1 and I know g, so that's going to be 2 times 9.8 times 20 meters. That's all under the square root. And so that's going to be 19.6 times 20. So that's going to be the square root of 392 meters squared per second squared. And when I take that square root, I end up with 19.8 meters per second for V2. So let's move on to one more example here, and we're going to talk about how potential energy turns into kinetic energy and vice versa. Okay, so I've got a situation here. It looks like a roller coaster. Let me make this a little bit bigger. A roller coaster, or a car that, one of those car tracks you make for a Matchbox car. But basically, we're going to put a ball up on top, and it's going to roll down, go through a loop-de-loop, and go up a hill and come back down. And we're going to say that the mass of this ball is 50 kilograms. All right, and there are 4 different situations we want to pay attention to. We have position 1, we have position 2 at the top of the loop, position 3 at the bottom of the hill, and then position 4 up here at the top of the little hill. And for each of those situations, we're going to find the potential energy, the kinetic energy, and the total mechanical, and either the velocity or the height. So for the first position, the object is 4 meters high, and it's not moving. So first of all, since it's not moving, we know that its velocity is 0. And if its velocity is 0, the kinetic energy is also 0. The potential energy is equal to mass times gravity times height. And so we just plug our numbers in, 50 kilograms times 9.8 meters per second squared times 4 meters, because it's 4 meters off the ground. And we multiply those numbers together and we get 1,960 joules. So right here, I've got a potential energy of 1,960 joules. Now remember, the mechanical energy that we have is the sum of potential energy plus kinetic energy. So I'm going to take 1960 plus 0, and I'm going to add those together, and that obviously should be 1,960 joules of mechanical energy. Now, I know that energy can't be created or destroyed, and that means that for each of the next 3 situations, the mechanical energy is again going to be 1,960 joules. All right, so let's go to position 2. Position 2, now, we're not as high as we were. The ball came down the hill and it came up to the top here. But at the top of that loop, it's only 3 meters high. So we're going to have a different potential energy this time. So let's figure out what that is. mgh, and that's going to be 50 kilograms times 9.8 meters per second squared times 3 meters. And in this case, it's not going to be 1960. It's going to be 1,470 joules. All right, well, I still don't know how fast it's going. I know it must have some speed now, because if it wasn't moving at all, it would just fall down. And so I know that potential energy plus kinetic energy equals mechanical energy. So 1470 plus what equals 1960? Well, let's just subtract. 1960 minus 470 equals 490 joules. So I know the kinetic energy. Now the last thing I want to find is how fast is it going? Well, the energy equation that I have for velocity is the kinetic energy equation. And it looks like this. I've got Ke equals 1/2 mv squared. There's that v I want. So I'm going to get that by itself by multiplying both sides by 2 and dividing both sides by m, and then taking the square root of both sides. And I'm left with v equals the square root of 2ke over m. And if I plug numbers in, I'm going to have 2 times 490 joules, because that's the kinetic energy we found over here, divided by my mass of 50 kilograms. And that works out to be 4.4 meters per second. So I'm going to put 4.4 meters per second in right here. All right, now, well, actually, let's go back here. So it started out at 0, it lost height, and as it loses height, it loses potential energy, but it's gaining kinetic energy. At the very bottom here, it shouldn't have any potential, it should all be kinetic, it should be going as fast as it possibly can, but then it starts going up this hill, it's gaining height, gaining potential energy, and losing speed, so it's losing kinetic energy, but again, the total amount doesn't change. Now after position 2, it's going to come back around. It's going to come lower and lower and lower, gaining kinetic energy, gaining speed, losing potential energy, till we get to position 3 right here. And in position 3, there is no height. So if there's no height, and our equation is mass times gravity times height, we know that there is 0 potential energy, 0 joules of potential energy. Which means that all of our energy now must be kinetic energy. And all of our energy is 1960 It's a weird 6. All right. So 1960 joules of kinetic energy. All right. Again, we want to find the velocity. I'm going to use the same equation I had up here. V equals 2ke over m. Square root of 2ke over m. And in this case, it's going to be 2 times 1960 divided by 50 kilograms. And in this case, that works out to be something like 8.9 meters per second. So notice, and the math bears it out, we said it was going 4.4 meters per second at the top of the loop, down here at the bottom 8.9. That should just make sense intuitively. Things go faster as they fall down. All right, now the last thing we want to find is the height here at position 4. And we're going to do that again by using our conservation of energy concepts. So in this case, we start out knowing what the velocity is. It's 6 meters per second. In order to find the height, I'm going to have to know the potential energy because that's the only kind of energy that involves the height. In order to find the potential energy, though, I need to know the kinetic energy, and I can find that from knowing the velocity. And so kinetic energy, again, equals 1/2 mv squared. And I plug in my numbers, 1/2 times 50 kilograms times 6 meters per second squared. And that's going to be 1/2 times 50 is 25 times 36. That's 900 joules of kinetic energy. Now if I have a total energy of 1960 and I have 900 joules of kinetic energy, the remainder must be right here. 1960 minus 900 is 1060 joules of potential energy. So from there, I can now find my height because potential energy equals mass times gravity times height. If I divide both sides by mg, I have an equation for height. Height equals PE over mg. So let's just put it over on the other side here. Height equals 1060 joules of potential energy divided by mass times gravity, divided by 50 times 9.8. And that works out to be 2.17 meters. So let's go up to the top here. This height is 2.17 meters. That's how tall that hill is. So again, roller coasters, pendulums, they're really good examples of showing the law of conservation of energy because they show how you're constantly changing from a lot of potential to a lot of kinetic to something in between, back down, back up. It's constantly changing, but the total amount of energy never changes. Now, in reality, if you go to Valley Fair and you watch the Wild Thing, or if you ride the Wild Thing, or any roller coaster for that matter, notice that the first hill is always the highest. And that's because, you know, you get in the train, it hooks up to a chain, it pulls you up to the top of the hill, and after that point, there's no motor making the train car go anymore. It's all gravity. And it's going to go down, and it maintains the same amount of energy. However, in the real world, there is friction. If there was no friction, you could make every hill just as high as the first hill, and you could make really long roller coasters that went on forever. But that obviously isn't the case. So every hill has to be a little bit lower because friction is always going to take away some of the energy. So we do lose some energy due to friction. The roller coaster and the car will lose energy. The Earth will not lose energy. The heat caused by friction, the sound made by the car moving, that heats up the atmosphere a little bit. The vibrations are absorbed by the ground, but the Earth as a whole still maintains all that energy. So anyway, that is potential energy and the law of conservation of energy. And that's all she wrote. Peace.